Hi everyone, I am Mohammad Adiban, PhD student at Norwegian University of Science and Technology, and today I'm gonna present our work Hierarchical Residual Learning Based Vector Quantized Variational Autoencoder for Image Reconstruction and Generation. This is a joint work with Kalina Stefanov, Marco Siniskalki, and Giampiero Salvi. Deep generative modeling has shown impressive results for the application of unsupervised learning in many domains such as image generation, arts, biomedical, speech synthesis, and etc. Variational autoencoders or VAEs as generative models encode the input data into the continuous valued representations by compressing information into a dense distributed embedding. Then the continuous representations are decoded in order to reconstruct the original input data. However, studies on human cognition emphasize the importance of discretization in representation learning. Discrete symbolic representation contribute to reasoning, understanding, generalization, and efficient learning. Vector quantized VAE, called VQ-VAE, was proposed as a discrete latent VAE model that relies on vector quantization layer to model discrete latent variable which quantizes encoder outputs to the nearest codebook vector, which is called codeword with online k-means clustering. The objective function of VQ-VAE aims at minimizing the reconstruction error of the input data while minimizing the quantization error in the embedding space. Such model can significantly reduce the amount of information required to reconstruct an image. VQ-VAE2 also was proposed to extend VQ-VAE by employing several layers, for example top and bottom layers of quantized representation to handle hierarchical information in images. In this case, top layers are responsible to model general information and bottom layers, which are conditioned on the top layers, are responsible to add more details. Different layers, however, share the same objective function, which does not encourage the layers to encode complementary information and resulting in efficient use of the codebooks. In this paper, we propose a hierarchical residual learning-based vector quantized variational autoencoder, namely HRVQ-VAE, for the image reconstruction and generation tasks. Our first contribution is a novel hierarchical vector quantization encoding scheme. Our method maps the continuous latent representation to several layers of discrete representation through hierarchical codebooks. In contrast with VQVA2, which randomly assigns code words in the codebook, in HRVQVAE, the vector selected within bottom layer determines the codebook that is activated in the top layer. Such a hierarchical searching procedure provides the advantage of local access to the codebook indexes, which dramatically reduces search time. Moreover, a novel objective function is proposed to provide contrastive learning by pushing each layer to extract information not learned by its preceding layers. At the same time, the objective function optimizes the output image from the combination of representation obtained from all layers. In order to generate new samples, the prior over the quantized representation can be modeled with an autoregressive model like PixelCNN with self-attention, which is called PixelSnail. The main idea behind these models is to leverage the chain rule probability to factorize the joint probability distribution over the input space into a product of conditional distributions for each dimension of data given all the previous dimensions in some predefined order. This order can be, for example, raster scan ordering. We conduct our experiments on four well-known datasets in computer vision. First, FFHQ. The dataset consists of 70,000 high-quality face PNG images at 1024 by 1024 resolution and contains considerable variation in terms of age, ethnicity, and image background. Second, ImageNet. The ImageNet project is a large visual dataset including more than 1.4 million images consisting of 1,000 object classes. Third, CIFAR-10. The CIFAR-10 dataset consists of 60,032 by 32 color images in 10 classes, with 6,000 images per class. There are also 50,000 training images and 10,000 test images. And finally, MNIST. The MNIST dataset, consisting of handwritten digits, has a training set of 60,000 examples and test set of 10,000 examples. Here the results are presented. Figure 7 shows the effect of number of layers in HRVQ-VAE on reconstruction's quality. We investigated different numbers of layers, namely from 1 to 6. Although all configurations have 64 code words in the final layer, we observed that increasing the depth of the model results in reconstructions with more details. Figure 8 provides a comparison with VQVAE2 on the effect of the model depth, or in other words, number of layers in terms of the reconstruction mean square error. The results demonstrate that increasing the model depth leads to better performance of HRVQ-VAE compared to VQVAE2. Furthermore, the performance of HRVQ-VAE improves consistently for all datasets with the increase in the number of layers. However, increasing the number of layers does not improve the performance of VQVAE2 for ImageNet and FFHQ from a certain point, and in some cases for MNIST and CIFAR-10 the performance decreases. Figure 9 illustrates the behavior of HRVQ-VAE and the baseline models, VQVAE and VQVAE2, with different numbers of code words. By increasing the number of code words up to a certain number, the performance of all models improves. Whereas HRVQ-VAE shows high performance, however, the efficiency of the baseline models starts decreasing from a certain point with increasing the number of code words, while the efficiency of HRVQ-VAE continuously increases for all datasets. This means that not only HRVQ-VAE does not suffer from the codebook collapse problem, but it also benefits from increasing the number of codebooks to improve performance. Figure 10 provides a visual example for Figure 9. As it can be seen in Figure 10C, by increasing the number of code words, VQVAE and VQVAE2 gets into the codebook collapse problem. However, it can be seen that HRVQ-VAE does not suffer from codebook collapse problem. We also evaluated our method for image generation. Figure 11 presents random samples generated by VQVAE2, VQGAN, and HRVQ-VAE. Due to the limitation in computational resources, the proposed model was trained with a smaller number of parameters. To make a fair comparison, we trained VQVAE2 using a configuration that is more similar to ours. It can be seen that the proposed HRVQ-VAE can generate more realistic samples, showing the superiority of our model. In order to conclude, we propose a novel multi-layer variational autoencoder method for image modeling that we call HRVQ-VAE. HRVQ-VAE learns hierarchical residual discrete representations in the iterative and hierarchical fashion. The objective of HRVQ-VAE is designed to encourage different layers to encode different aspects of an image. Through experimental evidence, we can show how HRVQ-VAE can reconstruct images with a higher level of details than the state-of-the-art models with similar complexity. And finally, we show that we can increase the size of the codebooks without suffering from codebook collapse problem that is observed in methods such as VQVAE and VQVAE2. Thank you all for watching my video. If you have any questions, please contact me.